I've also put that in announcement section. So today, I'm also going to show this. The date of the final is Monday, December 15. If you check the final exam schedule is updated. So the one I actually showed the other time is not correct. So the correct date for the final is what you're seeing right now. Is there anyone who actually see a date that is not this? Anyone? If you all see the same date as this, can I see your hands up? The same date as this. Okay, so thank you for that. So as students, you can go to maybe one stop or something, then you'll be able to see the final date for your exams. Okay, so this is a very crucial information that I want to pass across before I get started today. The date of the midterm still remain the same. Okay, one second. Okay, the last time I introduced you to probability on a finite sample space, and I actually remember that I, you know, gave you some kind of background information about why we find ourselves doing probability on finite sample spaces. If I can actually recall, I mentioned the last time that there's variations in the world, and because of that, whenever there's variation, and that we actually create room for uncertainty, okay, there is uncertainty about everything in this world. So how do we do a great job under uncertainty? How do we make predictions? How do we actually explain the process under uncertainty? Of course, we actually need statistical theory to be able to do that. And that is the reason why you are here. You really want to learn statistical theory that will be able to guide you in your decision-making process. Okay? Because in a stochastic environment, we make decision under uncertainty. So making decision under uncertainty could be very, very crucial, very, very crucial, and of course, is highly sensitive. Then we need to be able, how are we going to know the decision we're going to take is valid? Then the knowledge of statistical theory is very, very crucial. Now, you can't rule out, if you want to understand statistical theory, then there's always, you need to pay attention to probability theory, because in every statistical theory lies probability theory. So, and I told you the other time, probability thrives in variation. Now, in the process of trying to figure out the world, trying to understand the world, you need to, like I said, you need to be able to get yourself familiar with probabilistic structure. So, and of course, one of the things to let you know that we live in a world of variation is to consider sets. If things are the same, we do not need sets. What is the essence of sets? When things are the same. We only talk about sets when things are not the same. We have several elements, and of course, the elements in a set, and they can be distinguished from one another. And of course, I remember, oh, sorry, one second. So I remember I talk about using notation. In a statistical theory, we like using notation a lot. I remember I told you the other time, take a look at this guy. This is trying to say X, an element in a set, S. And of course, if you take a look at this other guy where we have one is an uppercase, the other one is also an uppercase, the sign in the middle represents a subset. So what this guy is trying to say right now is that the bigger set is S, the smaller set is A. So A belongs to set S. A typical example of that, I'm actually seeing A as this class. This class is a set of students, and I'm actually seeing S as the University of Minnesota. The University of Minnesota has a lot of students, and I'm going to say this class is a subset of the University of Minnesota. Now, I remember I also talk about giving you a composition of sets, okay? When we have different numbers, that's a set. We could have the combination of numbers and alphabet or different kind of stuff. We can also have a subset within a set. If you take a look at this guy, 0, 1, 2, okay, it's also a member of the set. Okay, so take a look at that. And let me tell you this guy, a 0, 1, 2, is a set on its own. A set can be a member of a bigger set. So 0, 1, 2 here is actually a member of the whole bigger set. That's exactly what I mean. Okay, now when you take a look at this, when you are seeing this, you're actually going to be seeing a typical real-life situation where there's variation. So there's a variation here. Okay, I also talk about an empty set. We're always going to have an empty set. An empty set has no element in it. And we have a notation for an empty set. Okay, we actually use this guy. The fact that we are saying this is actually saying that, probably maybe a class is empty. I want to believe before the first person arrive here, it's actually going to see an empty seat. So that's a typical example of an empty set. And let me tell you this, an empty set also has its own special notation. Okay, when you take a look at this is not a notation for an empty set. That is just indicating that a set without elements. But if I want to talk about the real mathematical notation for an empty set, is this guy here. So, like I said, in a world that is full of variation, we use mathematical symbols a lot. So, what I'm going to advise you to do, from time to time, is for you to be able to identify, what a particular notation represents in real life. We play with notations a lot. Okay, now let me tell you this. If there is no variations, there is no classifications. Okay? If there is no variations, there is no classifications. Okay? No variations actually implies no classification. Okay? But if there is variations, there is classifications. We're actually going to have classification within classifications. Now, I just walk you through set of numbers. Okay? And let me also tell you this. We're actually going to have classification. You know, there are some numbers, some numbers, they belong to a particular group. If there's no variations, all numbers will be the same. If there's no variations, all numbers will be in the same group. Now, because of that, we got some special notations that we actually use in classifying numbers, set of numbers. If you take a look at this guy that looks like an N, we call that guy a natural numbers. Natural numbers have sets. 1, 2, 3, 4, and so on like that. That's what I mean by natural numbers. We also have the one that look like a Z, okay, where we talk about a set of integers. We also have real numbers. The real numbers will be all numbers in this world, okay? So we're trying to tell you the classification, okay, of variation. The reason why there's classification is because there's variations. When you go to any clinic this morning, doctors doing a great job. Of course, they also deal with different kind of variations because those patients that visit clinic actually come with different disease, or some of them are even heady. So every individual is very unique in their own way. Okay, now we actually, like I said the other time, the reason why some students believe statistics is difficult is because of the fact that they don't get themselves familiar with notations. We play with notation a lot. Now, I want us to have a way to describe sets mathematically. How do we describe sets mathematically? I'm actually going to show you different method of classifying or describing sets. We have what we call a builder notation, and we have what we call listing. Okay? But what I'm trying to show you right now is what we call the builder notation. Now, pay attention to this. Okay? X lies in that. When you take a look at this X, that's a lower case, right? The fact that it's a lower case, qualify that to be an element. Okay? It's an element and not a set. So this guy, this particular X, is not a set. It's an element because it is a lowercase letter. Okay, in this course, when you see an uppercase letter, like this is an uppercase, right? That's a set. Okay, that's a set. So now, if you take a look at what I'm trying to say now, when you take a look at this guy here, I'm trying to say X lies, an element X lie in a set S. What we're trying to say is we actually have some condition on S. Okay, that means there's a condition on S. If there's a condition on X, that will translate into having a function. So because of that, this is going to be a function. Take a look at that. H of S means I'm having a function. I'm having a function. If I have an element, this is more or less like, X. Maybe that is the amount I get paid when I work for 1 hour. And if I work for 1 hour, how much am I going to get paid? If I work for 1 hour, which is X, then I'm going to get paid with H of S. H of S will now serve as a wage. which means I remember when you were in high school, when you talk about domain and range. Has anybody heard about domain and range? Okay, so when I have a hex, I'm going to have a y. Okay, so y now is the h of s. Y is the h of s. So y is actually going to be an image. Okay, and that's why you see h of s denote the image. We also call it range, and it's also a function h having a domain s. Okay, we're speaking mathematically now. But I really wanted to relate, that to real life. The moment you relate that to real life, you'll be, it's going to be so easy. So what does my x represent? Oh, my x represent probably the numbers of hours I work. And the h of s now represent the amount, or maybe in terms of wage, that I'm actually going to get. Okay, this kind of description here, is having, describing sets in a builder notation. Now, I need you to pay attention. We play with symbols a lot. We play with notation a lot. Take a look at this. When I say, for example, x lies in real numbers, this guy actually means x lies in real number. If I actually say x lies in real number, if I just write this guy, okay, this guy means x lies in real numbers, okay, then I'm trying to say s can be any numbers in the real numbers. But do you know at times I may want to put further information. If I now put further information, okay, just like the one you see now, and I say s greater than 0, so now I've added a new information. The new information I'm adding now, I'm trying to tell the world the x that I'm talking about should be strictly positive, non-negative. I'm not interested in negative. If I don't put this guy, then I'm interested in all numbers, positive numbers, negative numbers, including 0. But this guy is giving a further information that I'm not interested in ordinary numbers, but I'm only interested in positive numbers. Positive. I'm interested in positive numbers. Okay, go ahead.
The conditions, right? Can you make ands in the conditional part, so you can have multiple conditions?
That we can have a multiple condition?
Yeah, so x belongs to real number, given the x greater than 0, and some other condition.
Exactly. Yeah, we can also do that. We can give a further condition. Right now, when I say x greater than 0, I mean all positive numbers. And at times, I can say, even though they are all, I don't mean all positive numbers, I can say, okay, I mean a number between 1 and 10. So I can give a further classification. Does that make sense? It now depends on me. Good job. That's a good example. That's a good response. Okay, now, I want to move right now. We don't just do what we do. There's a reason why we do what we do. Math is easy. Math is like a story. Statistics is like a story. Now, we're building on something now. Today, we're going to play with notations a lot. And I need you to ask questions if you get stuck. We have been focusing on x. X that we're focusing on is actually an element. I'm talking about this guy, lowercase x. That's an element. Now, if I'm focusing on x, the other time I was talking about hours that I work, I want to believe there should be a kind of a range, okay, or the interval or the limit, okay, of the hours that I work, okay. Now, we want to talk about intervals. We want to believe every element should have a particular intervals. The same way that state of Minnesota has a boundary. At times when I'm driving, I'm just going to find, I'm going to look at the signboard. I'm going to see Wisconsin. Oh, I'm no longer in Minnesota. Every state has a boundary. Every element has an interval. Now, because of that, we want to talk about different kind of intervals, random variable S can have. And please, I need you to pay attention. Take a look at this guy. This is like open at both ends. When you see the normal parentheses, open at both ends, mathematically speaking, what we mean is that X lies in real number, but X lying between A and B. That was what you were trying to say the other time. At times, even though I'm talking about this condition, I can impose a further condition. What will enable me to impose a further condition is the use of intervals. Does that make sense? The use of intervals. So right now, this guy equation 1 mean S is greater than A, but less than B. But when you take a look at the second equation, okay, I have a different parenthesis now. Even though I'm still taking my S in real numbers, then it will involve some inclusivity, inclusive. You can see equality sign. Equality sign because of that guy. At times, we can have a situation where it's going to be open at one end and closed at the other hand. Where it is open, can you see that? Where it is closed, can you see that? And we can have situation where it is closed at A and open at B. Now, equation 1 to 4 will give you the possible intervals an element S can have. Does that make sense? But in all these situations, in all the equations, okay, we have a lower bound and the upper bound. The lower bound is A, the upper bound is B, then we expect A to be less than B. Does that make sense? Is there any question? Okay. Now, I quickly want to move right now. Now, I want you to see distinctions, excuse me, between equation 1 to 4. In equation 1 to 4, I'm only focusing on a situation where S is within intervals A and B. But what if in a situation where, if you take a look at equation 5, S lies in real number, but the upper bound here is not B. The upper bound here is infinity. Look at that. Then I'm going to say S lies in real number. This situation now is trying to say A is less than S. The lower bound is less than the random variable I'm focusing on. That's what equation 5 is saying. Open at both ends. Okay, we can have a situation where it is closed at A, open at that. I'm actually going to have this guy. There's a difference between A less than S and A less or equal to S. We could have a situation whereby we're going to start from the negative infinity all the way to the upper bound. Okay, and finally, when you look at equation 9, okay, equation 9, when you're talking about, oh my God, if you take a look at equation 9 now, equation 9, when I'm considering an open interval going from negative infinity to positive infinity, then I have the all set of numbers in this world, the real numbers. Okay? And that's why. But when you take a look at equation 5 to 8, even though we are still taking numbers in x in real numbers, but we give further information. But you take a look at equation 9, there's no further information. Equation 9 is strictly all numbers in this world. When you are considering between negative infinity and positive infinity. Now, because of the fact that in this world, if I actually have an input, there's going to be an output. And we want to believe there is a model that generates an output given any input. Because of that, we want to consider functions. Okay? We want to consider functions. Now, what do we mean by a function? We actually mean a mathematical rule, okay, that for each point in one set called the domain of the function, give a point in the codomain. Whenever there's an input, there's going to be an output. If I work for 2 hours, I'm going to get paid with this amount of money. If I work for 4 hours, I'm going to get paid with this amount of money. So which means whatever the numbers of hours that I work, there's going to be a corresponding the amount that I'm going to get paid. That is what this guy is talking about. Okay? And we need a functions, a mathematical function that we assign, to every single input, that we assign a corresponding output, okay, which we normally call for every single domain, we're actually going to have a codomain, for that. And to be able to have that, then we need a function that will do the mappings. And that very function, we can simply call it f, or we call it f of s. So f of s is a mathematical function that assigns numerical values to every element in the domain. It assigns a particular value in the codomain to every element in the domain. And because of that, we're going to call that a function of s. Okay? Which is f of s. I need you to pay attention. We're going to play with mathematics a lot. Now, if you take a look at this, I want to map elements in x to elements in y. Oh, x represents maybe I'm going to go from using hours work and wages to hours study and exam performance. As students, if you increase your study hours, what will be the effects on your exam performance? If I'm seeing X as the hours studied, and Y is the corresponding exam score, we want to believe there's a particular function F that is doing the mapping. Does that make sense? Which is exactly what I'm trying to show you here. Another way to write that is, if I map from X to Y, then there's a function responsible. The function responsible is actually what we call F, or we call that F of S. Does that make sense? So the element in S will be called domain. The element in Y will be called codomain. And the function we do a mapping, we map element in S to element in Y. That is what this guy is trying to say. Any question about this? Any question? Go ahead.
Y is the output, right? If you input something in the function, we get an output.
Yeah, Y is like an output here. X is like an input.
It's like Y is output, right?
Yeah. So Y is output, X is input, but to be able to have an output from an input, we need a function F. Yeah. That makes sense? Okay. Okay. So far so good, right? Now I want to move. Let me tell you this. If you really want to understand statistical theory, then you need to pay attention to symbols, notations. We've started, playing with notations, playing with symbols. If I were you, try to relate them to real life. What do they mean? I understand my mathematics perfectly because I'm able to relate symbols to real life. Today I've given a lot of examples. You can give your own examples. Okay, now we're talking about functions. We said if I want to go from X to Y, if I really want to map elements in S to elements in Y, then I need a function. Then I want to tell you there are different kind of functions we're going to have. Oh, function could be linear. Function could be quadratic. You've heard about quadratic function in high school. So I'm giving you an example of a function now that is quadratic in nature. You know what this guy is trying to say? F of s equal to s squared. What is that? Okay, what that guy is trying to say is, if I have a set x, and x, maybe I'm just assuming 1, 2, 3, 4, but this guy is trying to say f of s equal to s squared. F of s is the same thing as y. It means I just need to be squaring this guy. Does that make sense? So I'm able to determine elements in y, okay, by looking into the nature of the function. Without the function, I may not be able to correctly determine or compute elements in y. We need a function. So when function is quadratic, so this guy, what is it saying here? Oh, elements in S, the domain is X, but the image, after applying a function, is S squared, which is what we're saying here. Does that make sense? So we are mapping, that means that function map X to S squared. We can have situation where a function map x to x raised to the power 3 or map x to x raised to the power 4. We could have different kind of functions. Okay, another thing that I want to showcase, situation where we know what we have in x, right now, x, 1, 2, 3, 4, we know what we have in x, okay? How do we determine function? At times, function of s may be frequency, okay? At times, function of s may be quadratic. At times, function of s could be sinusoidal. It could be different kind, we have different kind of function. Right now, this f of s is trying to say 1 over 10 means maybe out of 10, I'm only seeing one time. Then the second one, 2 over 10 means I'm only seeing 2 times out of 10. I'm seeing 3 times out of 10, 4 times out of 10. In this kind of situation, the function here is frequency. Okay, function here means frequency, which means the numbers of times that I see a particular value of s. Now, I want to go further, and in that situation, it means I'm mapping 1 to 1 over 10, 2 to 2 over 10, 3 to 3 over 10, 4 to 4 over 10. Now, let's go more practical. If x represents different colors, okay, x, red, orange, yellow, green, and blue, okay, and the f of s now, okay, is trying to say, oh, tomato for red, orange for orange, lemon for that, lime for green, and corn for blue. So in this kind of situation, we are mapping, okay, the elements in S may not necessarily numbers. I told you the other time, when you talk about set may not necessarily be set of numbers. It could be a set of items. Does that make sense? And that's what you're seeing right now. At times, a function could be square root of x. Okay? A function could be square root of x. But whenever you're dealing with the square root of x, you need another condition. Because the square root of a negative, it's not going to make sense. If you have a calculator right now, if you plug in square root of negative 16, I want to believe your calculator will flash an error. So, and that is why here, okay, if my f of s is the square root of s, then I have to write a restriction. It's not going to be all s in real number. It has to be strictly positive, 0 or greater than 0. And that is exactly what we mean. Go ahead.
So can't like a function have imaginary output? So for example, if you put that condition, it'd be negative root.
Yeah, so it's not going to make sense because we actually want to deal with real numbers. Otherwise, without that condition, just like what you said, it's going to have an imaginary output.
Yeah, it makes sense for that. But like in like mathematics, they probably like use some functions which have like imaginary.
Yeah, so that's a good one. But I'm going to emphasize on this. We care about real numbers. We may not be able to care about imaginary, and that is why a further condition is required. So if you take a look at that, I said x greater than or equal to 0, and that was why I said without the domain indicated, the definition makes no sense. What is the domain indicated without this guy here? Without saying, because if I just, then this is not defined for all x in real number. Because when you press the square root of negative 16, then it's going to give you error. Does that make sense? Okay. Now I want to move right now to something else. I need you to pay attention. Because there's variation in this world, there's also variations in functions. I've talked about quadratic function, I've talked about square root function. I want to go into exponential function now. Okay? I want to go into exponential function. Okay? You know, you have a real number, you have some values in real number, and you have some values in real number, and you actually want to map, and using a function of exponential, okay, the final result is actually going to be 0 and infinity. So what I'm trying to say, real numbers, when I say real numbers, negative, positive, okay, 0, if you do the exponential, if f of s, for instance, I have exponential raised to the power x. If you take your calculator, put any number here, any number, whether negative or 0 or positive, then it's going to fall here. So when I do the exponentiation of numbers will give either 0 or will give the number between, within this. Exponentiation of numbers is not likely going to give you a negative. So that is what this guy is trying to say. Okay, so the function that I'm using now is exponential raised to the power x. So which means I want to map from x to exponential raised to the power x. But do you know, if I can go like this, I also want to go backward. Going backward now is, I want to go from here back to that. How can I recover that? Then I'm actually going to perform a logarithmic operation. If you take a look at this, if I take the log of exponential, if I take the log of this, so naturally, if I have the log of exponential, okay, and I'm doing the logarithm to that. So what would this guy going to give me? X log of E. The log of E is 1. This is x. The way I can recover my x back, if I have exponential raised to the power s, I can recover my x back by taking the logarithm of exponential. The logarithm of exponential is what we call natural log. We call that natural log. Another name for logarithm of exponential, we say ln. Has anybody seen that before? Ln? That's a natural log. So So if I have 0 and infinity, and I take the log, for your information, the domain cannot be negative. If you take the log, you want to try that? What is the log of negative? Do you want to press your calculator? Log of negative may be indeterminate. And that's why it has to be 0. It has to be, the domain has to be this. So that, when you take the log of those numbers, then it can give you any number in this world. That is what this guy is trying to talk about. We also have other functions. Now, this is what I was explaining the other time. Logarithm of exponential of s is x. Exponentiation of logarithmic s is also x. You can try this mathematically. Okay, I want to move right now. Now, I've talked about all of that. Okay, now, do you know that we can also have a constant function? Today we've been discussing function. Okay, we've been discussing function. Okay, you know, if you take a look at this guy, S tends to C. Okay, take a look at that guy. Okay, maybe my f of s equal to 5. Okay, for whatever values of s, y remain the same. Let me tell you this. Maybe I don't like watching a particular game, and you say, oh, Professor, let's go and watch the game. And I said, no. Okay, Professor, I'm going to give you $5,000 if you go with me. And I said, no. Whatever you say, I said, no. That's a constant function. It remains the same. For any value, when s changes, y remains the same. That's a constant function. Does that make sense? So we could have constant function. Then another function I want to talk about is identity. Identity function. Identity function, okay? Identity function, okay? When you preserve a process, okay? You have a situation where inputs actually give you the same as output. Input and output is the same. Okay? In that situation, take a look at that. X to x. In that situation, if I have x and y, if this is 1, 2, 3, 4, 5, this is also going to be 1, 2, 3, 4, 5. That's an identity function. You can have identity function. Very useful in computer application, okay, where you actually want to conserve or preserve a particular input, okay? So we have an input. So in this case, I wanted to see the difference between constant function and identity. Okay, for x and y, if this is 1, 2, 3, 4, 5, oh my God, this guy is going to remain the same, all true. That's a constant function, but this is an identity function. But the bottom line is this. Understand the functions you are using. There are different kinds of functions. That is the bottom line. Okay, I think I've explained all of that. Now, the next thing that I want to talk about, probability model. Now that we understand different kind of functions, we understand different sets, we want to talk about probability model. Let me tell you this. Probability model is a mathematical framework that we use to represent random phenomena. Okay, in a stochastic world, we have random events. So the mathematical model, okay, the mathematical framework, and that is going to come in terms of probability distribution, okay? So the mathematical framework that we use in doing that is what we call probability model. And let me tell you this. How can I specify my probability model? Okay, probability model can be specified using probability mass function. When I talk about probability mass function, PMF, I want to focus on discrete random variables. Okay, as time goes on in this class, I'm actually going to tell you that we have different type of variables. Okay, we got discrete. Okay, we got continuous. We have a probability distribution for discrete. We have probability distribution for continuous. So the name of the probability distribution for discrete random variable is called probability mass function. The name of the probability distribution for continuous random variable is called probability density function. So I'm actually going to say this. Probability model will look like a probability function. Probability function is different from quadratic, is different from logarithmic, is different from every other function we talk about. Because we actually going to impose a further restrictions on that as time goes on. So we have a distribution function, we have a probability measure. You know, it's just like what are the things that I can use to identify a state? Oh, state of Minnesota. What make a state of Minnesota to be different from state of Illinois? Oh, in Minnesota, there used to be like the weather. If you look at the weather, at times very harsh. Oh, in the state of Minnesota, there used to be this, there used to be that. We also have the same in probability model. I want to identify a particular real-life situation, and I want to specify probability model for a given situation, then what am I going to use? It could be probability mass function, it could be probability density function, it could be probability measure, it could be expectation operator. We're still going to do all this. Now, please pay attention. I want to start with probability mass function. What do we use probability mass function to do? Probability mass function is a probability model for discrete variables. What do I mean by discrete variables? Oh, the variable that can be counted, like the number of students in this class. Okay, the numbers of goals scored in a football or scored in a soccer match. Okay, something that can be counted. The number of children in the family. Okay, if I really want to figure out, if I really want to understand uncertainty around discrete random variable, what am I going to use? I will use a probability mass function, PMF. And in that situation, I have a set S. And when I have a set X, then there's going to be a function. That F is PMF that we map from that set to real numbers. And let me tell you this. Because probability model, okay, defined by probability mass function, requires, according to the Kolmogorov axioms, okay, according to Kolmogorov axioms, okay, when you're talking about probability function, it has to be non-negative. And that is why you see f of s greater or equal to 0. F of s greater than or equal to 0, okay, it's a condition we are imposing on probability function because probability of an event should not be negative. It can be 0 or greater than 0, and that's why you see that. Does that make sense? Okay, and it must sum to 1. Summing to 1, okay, I talk about Kolmogorov axioms. The first one, where f of s is greater or equal to 0. Please pay attention. Okay, where f of s is greater or equal to 0, we call that non-negativity. That is non-negativity axioms under Kolmogorov axioms. The second one, this guy is saying sum of probability must be equal to 1. That is what we call normalization. Okay, summation f of s equal to 1. That is normalization. Normalization. Okay, under Kolmogorov axioms, the probability function, okay, the properties of probability function could be it should be non-negative, then it should be normalized, meaning that the sum of the probability must be equal to 1. That's what it means. Wait a minute. 9:05 to 9:55, we're done. Okay, that's all what I got for you today. Gonna see you on Monday. Have a nice weekend.